This video is for the revision of kinetic theory of gases. Okay, there are two important theories here. The first one is the gas consists of particles of molecules with negligible size or volume. So the size or volume of the particles are negligible. We'll look deeper into that later. And the gas particles have negligible intermolecular forces. These are theories for ideal gases. So if those gases are ideal, of course, they're not real gases. In an ideal world, gases have no size or volume and no intermolecular forces. We'll never get it to be fully ideal, but it can be as ideal as possible. Okay, these ideal gases also, the particles are in constant random motion. The collisions are perfectly elastic and the kinetic energy is proportional to its absolute temperature. Okay, but we'll focus on the first two. Let's look a little deeper into that. What volume or size are they talking about? So if we have an ideal gas here in this container, the one that is negligible, they're not talking about this container here, the size or volume, not of this container, but of the gas molecules. So this volume or size, this volume, this volume, this volume, this volume is negligible. So it means that this whole container, the whole volume in this is what the gas is, the size that the gas is occupying. So we neglect the size that the molecules actually takes up. That would also mean we neglect the fact that N2 has different size with H2, and they have different sizes with NH3. So no matter what gas we have, they're supposed to occupy the same volume here, because we actually ignore the size of these. Some are bigger and some are smaller, actually, in actual fact, in the real world. But in an ideal world, we treat as if they all have the same size, which is negligible, almost no volume, and they just occupy the same volume here. So if I have a mole of N2 or a mole of H2 or a mole of NH3, they will all occupy the same volume. That is in an ideal world. So in STP, this is available in your data booklet. 1 mole of any gas is going to occupy 22.7 dm³. This is from the IBDP data booklet. Okay, the other thing is that these gas, which are ideal, they have no intermolecular forces. So it's not really true, but in an ideal world, it's true. So like H2 and H2 here, we neglect this intermolecular forces very, very, very weak till we can neglect it. Okay, but it's actually not so true for like NH3, because NH3 has a rather strong intermolecular forces. So in comparison, I would say that H2 is probably more ideal than NH3, because NH3 has a very strong intermolecular forces, which is not negligible. H2 may be a little weaker, we can neglect the intermolecular forces. So as you can see, it can be more ideal or less ideal, but it can never be fully ideal. According to Boyle's law, for an ideal gas, its volume is going to be inversely proportional to its pressure if we do this in the same temperature, so constant temperature. Okay, let's say I have some gas in here, 1, 2, 3, 4, 5. So this is at first, and I keep the temperature the same, and I push this down. Okay, what's going to happen is the volume will decrease when I push this down. So volume will decrease, but the pressure will increase, because at first these molecules will bounce and move around randomly in this larger space. So it will exert some pressure on the wall of this container. And when I press this down, now it has less space to bounce. So it's going to exert more pressure. So the pressure has increased here, but the volume has decreased. This means that P times V, it's actually a constant. So when this volume decrease, the pressure increase. Volume decrease, pressure increase, and it'll come back to the same reading here. Okay, so if that's the case, PV equals to a constant, I can also say that P1 V1 equals to P2 V2. What does that mean? The pressure here, multiply the volume here, which is larger, is equal to the pressure here, which is higher, multiply by the volume here, which is smaller. So it's going to be a constant. Now, if I were to plot a graph of V and P, since it's inversely proportional, so it will look like that. But what is V directly proportional to? So if I have V 1 over P here, then it'll be a straight line. What if I were to plot PV versus P? So when I increase the pressure, what happens to PV? So when I increase the pressure here, the volume is actually going to decrease and it's going to balance out. So I'm still going to get the same value. So no matter how I increase the P, let's say here, it's still this value. And I increase the P again, the V will decrease further and I'm still going to get the same value again. I increase the P again, the volume will decrease again. I'm going to get the same value again. So this way, constant straight line. Next, Charles' law for an ideal gas is the volume is going to be proportional to its absolute temperature. Absolute here means this must be in Kelvin and not degrees Celsius. This is when we keep the pressure constant, so we don't disturb the pressure, we keep the pressure the same. Let's say if there's gas in here and I heat it up, so after heat, we want the pressure to be the same. We don't want it to exert more pressure. So to balance that out, the volume would increase if you increase the temperature. So if it's directly proportional, I can write it this way. I can bring this down. So V over T should be a constant. What does that mean? As temperature increase, volume will also increase. It's a constant. So at initial volume, this is the initial volume, at a certain temperature, if I were to increase the temperature here, heat it up, then it will move to a bigger volume. So new temperature, which is higher, it will cause the volume to be also higher. So it sort of cuts off, you'll get a constant. Let's look at the graph. So V versus T at, we are using absolute temperature, so that's Kelvin. You'll get a direct proportional graph. But if you were to plot it in degrees Celsius, then the graph should go back this way. So this is 0 Kelvin. And if this is in degrees Celsius, here is 0 Kelvin, so it's negative 273 degrees Celsius. This is 0 degrees Celsius. Next, pressure law. For an ideal gas, pressure is directly proportional to its absolute temperature. Again, we need to convert that to Kelvin to make this work. And the volume needs to be constant. So again, this gas container, 1, 2, 3, 4, 5. Again, I'm gonna heat this. 1, 2, 3, 4, 5. So if I heat it, by right, the volume would increase, but we're gonna keep the volume constant. So I'm gonna press this so that the volume stays the same. So if that's the case, there's more heat, more energy, they're gonna move more, and they're gonna hit harder on the wall, exert more pressure. So the pressure increase accordingly, directly proportional to the absolute temperature. Therefore, I can say P equals to KT. I bring the T down. P over T would be a constant. So P1, T1 over T1 here. That's the pressure here and the temperature in here. And when I change the temperature, I heat it up. So T2 is higher. T2 is higher, the pressure would also be higher. So this cuts off, you'll get the same value again. So P2 over T2 is also K, same as T1 over T1. And the graph, P on this side, T if it's in Kelvin, so we'll get one that is directly proportional. That's 0 here, 0, 0 here. And if it's not in Kelvin, but degrees Celsius here, then it goes behind like the other graph. And this is negative 273, which is also 0 Kelvin. Let's combine all three laws. So this one, P1 V1 equals to P2 V2. V1 over T1 equals to V2 over T2. And P1 over T1 equals to P2 over T2. We'll get P1 V1 over T1 equals to P2 V2 over T2. That equals to a constant. Okay, so that constant, we'll give it R as a symbol. That's for 1 mole of gas. So if you have n moles of gas, then just multiply n. Okay, so I'll rearrange that, bring the T up, and I'll get PV equals to nRT. Remember the units. P must be in Pascal, V meter cube, N is the number of moles, R is given in your data booklet, and T must be in Kelvin. Remember to convert your units. What about the unit in P1 V1 equals to P2 V2? In this case, you don't have to convert the units if both sides have the same unit. So for instance, if you have Pascal here and Pascal on this side, so that's fine already. But let's say you have centimeter cube here. Are you supposed to convert that to meter cube? Now, if the other side, you also have it in centimeter cube, it's fine because it will cancel out. So as long as the left and the right have the same units, then you don't have to convert the units. For the second one, you have to convert the T to Kelvin, but you do not have to convert the V to any specific unit. So both sides needs to have the same unit. If you have centimeter cube on this side, you must have centimeter cube on this side. If you have meter cube on this side, you must have meter cube on this side. It cuts up. So both needs to be in Kelvin here. Same goes for pressure here. If you're gonna use Newton per meter square on this side, then use Newton per meter square on this side. If you're gonna use Pascal on this side, then use Pascal on this side. If you use kilopascals instead, then use kilopascals on this side. Okay, but for temperature, you must convert them to Kelvin no matter what. But for PV equals to nRT, you must use these specific units in order to get the correct mole. Okay, a gas behaves more ideal and it fits this PV equals to nRT when it's at low pressure or high temperature. So at low pressure, so it has more space to move, that its own size is negligible. And at high temperature, it will move so fast, it will not interact with the other particles. Okay, so what makes it not ideal when it's at high pressure or low temperature? Let's have a look at that. Okay, at high pressure, so let's compare one that is low pressure. 1, 2, 3, 4, 5. And at high pressure, 1, 2, 3, 4, 5. So according to the kinetic theory of gases, we know that it's ideal if the volume or size is negligible. So let's look at the first container. The size of these particles compared to this whole container that it occupies, the percentage of the volume here is low. Okay, now there is a smaller container now. So the pressure is higher here. And the volume that these particles have compared to the volume of the container is now at higher percentage. So this is less ideal because the volume cannot be neglected anymore. So at higher pressure, gases are less ideal, or it deviates from being ideal. Also look at the space between the particles. So at higher pressure, they are closer to each other, then they will probably start to interact with each other, and they'll have some attractive forces, which means it's not so ideal anymore because ideal gases have no or negligible intermolecular forces. Let's look at temperature next. Okay, at low temperature, they're closer to each other because it will move slowly. And at high temperature, they're just moving everywhere like I showed you just now. Okay, but at low temperature, they start to slow down and they'll move in and out of each other next to each other. So they start to have attractive forces between each other. So if they have intermolecular forces, then they are not so ideal anymore. So when it's not ideal, then PV equals nRT is not accurate anymore. So that assumption is only for ideal gases. What about polar molecules? So if I'm comparing something like helium, helium has a small size and have very weak intermolecular forces. No one side is more negative or positive. So this is probably more ideal than something like ammonia, where N is very negative and H is very positive. So with another NH3 here, it will probably be attracted. So a negative is attracted to this positive because this is a polar molecule. So if it's a polar molecule, it will have more intermolecular forces, therefore less ideal. It doesn't fit the kinetic theory of gases. Let's look at Dalton's law for better understanding of gases. If I have three gases mixed in a container, let's make one green, 1, 2, 3, and one red, 1, 2, 3, 4, and another one yellow, 1, 2, 3, 4, 5, and say in here it's 2 kilopascals, the pressure. Okay, the total pressure that's exerted by the green, the red, and the yellow will be 2 kilopascals. So what's the partial pressure of each of these gas? The partial pressure exerted by the green, the red, and the yellow is proportional to like the mole ratio. So for example, I have 3 pieces of this green ones, 3 plus 4 plus 5. So there's 12 in there, for example. So 3 out of which is the green one over 12. So let's say that's the mole ratio here. So I have the moles of the green one over the total mole times multiply 2 kilopascals. That would be equal to the partial pressure exerted by the green particles. That would be quarter of 2 kilopascals. So 0.5 kilopascals. As for the red ones, there's 4 of them. So 4 over 12 times 2 kilopascals. That's the partial pressure of the red gas. So I got 0.66667 kilopascals. As for the yellow ones, 5 over 12 times 2 kilopascals. So the partial pressure is 0.8333 kilopascals. If you total these up, it's going to be 2 kilopascals. So we can say that if you have the mole of A over total moles, it will be equal to the partial pressure exerted by that gas over the total pressure. Let's try a PV equal to nRT calculation. So this is an ideal gas. If it's not ideal, then we can't use PV equals to nRT. Okay, what information did they give us? They give us the V. M, oops, M was not in our PV equals to nRT. There is the T, but we need to convert that. And there's the P. Okay, so we want to calculate the MR. So PV equals to nRT. How is number of moles related to M? So M over MR equals to number of moles. I'm going to replace that. So PV equals to M over MR, RT. Now I can move it to the other side. So MR equals to MRT over PV. So I've got all the information I need. MR equals to mass R T over P. Oh, and V, I need to change that to meter cube. Okay, let's calculate that. So I get around 131. That would be the MR. Next example, this time they gave us density. Density would include the mass and the volume here. I'm going to use that same thing again. MR equals to MRT over PV. So this is density. Let's calculate that. 3.17 grams in a dm cube. So in a meter cube, it will be more. So that's M over V already. R and T over PV. V is already settled, and P kilo, so I want it in pascals. There you go. So I got around 97 gram per mole. Okay, I hope you already get the idea. Let's try the last one here. There's the T, there's the P. Again, we have the M and the V together. Calculate the MR. MR equals to nRT over V and P. This is the density. Let's fill that in. So I got around 28 gram per mole.